Welcome to our tutorial class. Today we are going to look at organometallic chemistry, and our tutorial is going to focus on 18 electron rule. In this rule we are going to look at the two types of rules. One is the neutral ligand method, sometimes called as the covalent method, and the second rule is the donor pair method or the ionic method. We are going to look if these complexes that we have really obeys the 18 electron rule. So the 18 electron rule simply says that the sum of the d electrons possessed by the metals plus the electrons donated by the ligands should add up to 18. So it means that if the complex does not have 18 electrons, then it does not obey the 18 electron rule. But if it has 18 electrons, then it obeys the 18 electron rule. But before we start, it is very important to know the types of the ligands that you are going to deal with. So if you check, we have the L-type ligands and the X-type ligands. The L-type ligands, for example, like the carbonyl and the phosphine, contribute to 2 electrons each. So it means that if I have 2 of the carbonyls, it will be 2 times 2, and that's going to give me 4 electrons because each carbonyl contributes to 2 electrons. And each phosphine also contributed 2 electrons. These are some of the L-type ligands. We can also have the X-type ligands, and some of them includes the halides. Example of the halides like bromine, chlorine. And another X-type, we have the hydride, we have the cyanide, and we have the methyl. And each one of them, the X-type, a neutral ligand method, they contribute to 1 electron each. So if in case, for example, I have 2 chlorine, so it's going to be 2 times 1, and that's going to give me 2 electrons. So sometimes we can also have the cyclopentadienyl, and we can also have the benzene, but in that case, especially in the neutral ligand, we are going to look at the eta number. We are going to look at the concept of hapticity and the eta number. So this 5 tells us the possible number of atoms that can be the ligand can connect to or can link to the metal. And in this case of cyclopentadienyl, the eta number here is 5. So in this penta-aptocyclopentadienyl, it can contribute to 5 electrons. In the case of the benzene, in which we are going to have the C6H6, and the hepta 6 is going to contribute to 6 electrons. So now, this is very important to know. The L-type, the types of the ligands are very important to know before we start looking at the 18 electron rule in each and every category of the types. So now we are confident of the types of the ligands. Now we can start. So we're going to start with the neutral ligand method, and in this method, all the metals have been assigned an oxidation state of 0, so that's why you see that you have put the oxidation state of the metal. So the first thing that we need to know is that the metal that we have, which group does it come from? And that one is going to tell us the number of the electrons that it can contribute. So for example, we have the ion, so we say now our ion is from group 8, so it's going to be D8, so meaning that it's going to contribute to 8 electrons. And how many carbonyls we have? The type of the ligand there that we have is the L-type. So we have the carbonyl, which is an L-type, and each L-type contributes to 2 electrons. And how many are they? We have 5 of them. So we're going to say 5 times the carbonyls, so that's going to give us 5 times 2, that is 10 electrons, and then the total here is going to be 8 plus 10, and that is 18 electrons. So it means that this complex that we have here is stable because the sum of the electrons, that is the 8 electrons given by or possessed by this metal ion, plus the 10 electrons donated by the ligand carbonyl, give us 18. Let's look at this complex number 2. In complex number 2, we are going to follow the same criteria. We have to write the metal and the d electron counts of the metal. Manganese is in group 7, so it is D7. So it means that manganese is going to produce 7 electrons. And the next thing we have to write is our ligand. In this case, it is carbonyl. And carbonyl is the L-type ligand, and each L-type ligand contributes to 2 electrons. And how many carbonyls do we have? We have 6. So we're going to say 6 times that one. So we're going to have 6 times 2, which is going to be 12. So I'll just write here 6 times 2, which is going to give us 12 electrons. So how many electrons do we have in total? We have 7, we have 12, that is 19 electrons. So we have 19 electrons. So it means that this complex number 2 does not obey the 18 electron rule. So this does not obey the 18 electron rule. So no matter how many ligands you have, let's say you can have the phosphine, you can have the X type, you need to put and account each and every one for them and add the sum of the total electrons. In second category, we are going to look at the complexes with a charge. Sometimes we find that the overall complex has a charge, and there are two things that we can do. If the charge is minus, the overall charge is minus, it tells us that this complex has gained some electrons, right? But if the charge is positive, then it tells us that the complex has lost electrons. So positive, the charge has lost electrons, and negative, the charge has gained electrons. So it means that when it is negative, we are going to add the number of electrons based on the charge that we have. So if we have, let's say, minus 2 as the overall charge, so meaning that we are going to add 2 electrons. But if we have, let's say, positive 3 as the charge, then we are going to subtract 3 because it has lost those 3 electrons. The same thing in this category, we are still going to follow what we did in category number 1 or in complex 1 and 2, but now we have to take into account of this charge that we have here. So we're still going to say our ion, which is in D8, so it will contribute to 8 electrons. Then we have the carbonyl, which is an L-type ligand, which will contribute to 2 electrons per each carbonyl. And how many are they? They are 4. So 4 times 2 will give us 8 electrons. And we have minus 2, and that's going to make plus 2 electrons. So this minus 2 charge tells us that it has gained 2 electrons extra. So let's count. 8 plus 8 is 16. 16 plus 2, that is 18. And therefore, that's 18 electrons. And it has obeyed the 18 electron rule. This also obeyed the 18 electron rule. But this one did not obey the 18 electron rule. Now, in this case, now we have seen where the overall charge or the complex with the charge, the overall charge is negative. Let's look example number 2, where the overall charge is positive. We have said when it is positive, it means that the complex lost certain charges, and we are going to subtract those charges that it lost. So manganese, we know it is in D7, so it's going to contribute to 7 electrons. Carbonyl is our ligand here, and it is L-type, so it's going to contribute to 2 times the number of carbonyls present. And how many carbonyls present here? There are 6. So 6 times 2 is going to be 12. Oh, sorry, let me put this is 6. This is 6. It should not be 2. So this is 6. So 6 times 2 is going to give us 12 electrons. And then we have positive. Then we have positive 1 there. So meaning that you're going to subtract 1 electron because it lost 1 electron. So let's add the total electrons that we have. We have 7 plus 12 is 19. 19 minus 1 is 18. So we have 18 electrons, and therefore this complex obeys the 18 electron rule. Remember, in this case, it did not obey electron rule in this case. All right. So this is how we can perform neutral ligand method or covalent method when we have either when the complexes are charged or when the complex has overall charge of 0. So let's look what is next. So in our next video, I try to draw these diagrams. Sometimes you can have a complex in which there's a bond between metal are bonded together, and we have to account for them towards the 18 electron rule. So in this case, in this case, we have to look at one metal at a time. For example, first, so how many metals do we have here? We have 2. Let me change the ink in this case. So we have this metal here, metal number 1, and we have metal number 2, this one here. So if you see, this metal here is rhenium. So if you look at these 2 rhenium metals, they are connected with this bond. So we have rhenium bond, okay, and each metal bond contributes to 1 electrons. So in this case, we have rhenium bond, which is only 1 bond, so it will contribute to 1 electron. But also, let's arrange them in order now. Rhenium is in which group? Or let's check our periodic table. Rhenium is also in group 7, so it's gonna be D7, so meaning that it will contribute to 7 electrons. But then, how many carbonyls do we have here? Look, this is how we write this complex here. So we have 2 rhenium and we have 10 carbonyls. What does that tell you? It tells you that there's a rhenium bond, and in each rhenium we have 5 carbonyls. So let's look. Let's take this rhenium on the left hand side, this one, okay? How many carbonyls do we have? We have 1, we have 2, we have 3, we have 4, and we have 5. So we expect the same number of carbonyls, because it's symmetrical. We have to expect the same number of carbonyls on the other rhenium metal. And let's look. In this one, we also have 1, 2, 3, 4, 5. So each rhenium metal has 5 carbonyls, and then we can introduce our ligand now. So we have 5 times, so that's carbonyl. And remember, carbonyl is L type, so it's going to contribute to 2. So 2 times 5 will give us 10 electrons. Rhenium is going to give us 1 electron. And rhenium is in the group 7, so it's going to be D7, which is 7 electrons. So let's add them together. So 7 plus 1 is 8. 8 plus 10 is 18. So we have 18 electrons, and this obeys the 18 electron rule. So let's look the one on the right hand side. This is B. So this is cobalt. So we have cobalt, and we have 4 cobalt bonds, and our metal here is cobalt, and then we have 12 carbonyls. Okay, what is the one in black are the metals, which is in this case is the cobalt. So we have how many? We have 1, 2, 3, and 4. So we have 4 cobalt metals, just like we have. And I want us to focus on each metal at a time. So I'll take this one as our metal of focus. So if I look at this metal on the right hand side, this one, this is our metal number 1, and this our metal number 2. We can see it is connected to it, and we can see there's also another bond connected to it. So this is number 3. So it means that cobalt bond is 3. There are 3. One cobalt metal is connected to 3 different cobalts. So even if we take this one as our focus, okay, then it is connected to this one, that is 1. It is connected to this one, that is 2, and it is connected to this one, that is 3. Okay, so it means that each cobalt metal is connected to 3 different cobalts. So it means that cobalt bond, I'll put it here, cobalt bond is 3. So that's 3 electrons. And let's look at the number of carbonyls. Let's put the number of carbonyls. So let's check each cobalt or each metal at a time. So I'll start with this one. I have 1 carbonyl, 2 carbonyl, and 3 carbonyl. So each metal is bonded to 3 carbonyl ligands. Just like even if I take this one here, I'm gonna have 1, 2, 3. So that's 3 Even if I take this one, 1, 2, 3, even this one is 1, 2, 3. So it means that each cobalt metal is bonded to 3 carbonyls. So we have 3 times that carbonyl, and that's going to give us 6 electrons. And let's look at the cobalt. Yeah, everything is CO. Okay, let's look at the cobalt. Cobalt is in which group? So let's look. Cobalt is in D9. So cobalt is in D9. So it's going to contribute to 9 electrons. Let's look. Yeah, this is all what we have. So let's look at the total number of electrons. 9 contributed by the cobalt plus 6 contributed by the carbonyls ligand, that is 15. Then 15 plus 3, which is the metal bond, is 18. So we have 18 electrons, and this is obeys the 18 electron rule. The most important thing to focus on in this part is to check. First, take one metal and take it as the point of reference or metal of reference. Then from it, look how many metals are directly bonded to it. That's going to give you the number of metal bond. And then take one metal at a time. Look how many carbonyls are bonded to it. Then that's how you're going to get the number of carbonyls per each metal. So that's how we can perform this step of, in this case, when we have metal bonding, and that's how we can get the total number of the electrons in that complex. So in this case, we are going to look at the bridging carbonyls. So with the bridging carbonyls, it means that we have known that carbonyl contributes to 2 electrons. So it means that if one carbonyl is bonded to 2 different metals, and these metals are also bonded together, so we have metal bond, but of these 2 metals, they are also connected with one carbonyl. Remember, carbonyl is an L type and it contributes to 2 electrons. So it means that the carbonyl will contribute 1 electron to each metal it is bonded to when it is a bridging. So it means that if we have one bridge, it's going to contribute to 1 electron. If you have 2 bridges, then we are going to have 2 electrons. So our metal here is cobalt. And we have seen cobalt is in D9. So let's identify our bridge. So this is our metal, but then we have this carbonyl here. This carbonyl is bonded to this metal, and it's also bonded to this metal. So it means that into each metal it contributes to 1 electron. So this is our first bridge. So we also have our second bridge, which is also connecting this metal on the left and also this metal on the right. Okay, so let's see. Our metal here is cobalt, so we're gonna see cobalt is in the D9. We have seen that. And then we have the carbonyls. So remember, cobalt is C, capital C, small o, but carbonyl is capital C, capital O. So our carbonyl here, there are how many? Let's take one metal at a time. I'll take this one. So 1, 2, 3. And also let's take the other metal on the left. 1, 2, 3. So each metal is bonded to 3 free carbonyls. So that is 3 times each carbonyl contributes to 2. So we're gonna have 6 electrons. This is D9. And then we have metal bond. So we have cobalt bond, and it's 1, so it's going to be 1 electrons. And then we have 2 carbonyls bridge, and that's going to give us 2 electrons. So let's add them together and see how many electrons does it have in total. So 9 plus 6 is 15. 15 plus 1 is 16. 16 plus 2 is 18. So it means that it gives 18 electrons, and that follows the 18 electron rule. When it has been assigned the oxidation number of 0, there still contributes to 2 electrons. Okay. The X type, where we have the alide in, for example, the bromine, the chloride, and they are assigned an oxidation state of -1. Okay, we also have the hydride in -1 state. We also have the methyl. Everything in the X step has been charged an oxidation state of -1. What does that tell you? Remember, initially in the neutral ligand method, all the X type were contributing to 1 electron. So we assume that now they have 1 electron already. Now they have been assigned an oxidation state of -1. So they have 1 electron extra. So in total, when we're looking at the donor pair method of the complex, the X types are going to contribute to 2 electrons each. Okay, so it means that if I have chloride ion, it's going to be 2 times 1, and that's going to be 2 electrons. But if I have 2 of the chloride, it's going to be 2 times 2, which is 4 electrons. So be very careful with the type of the ligands and in which type of the method are you using. Now, you remember cyclopentadienyl, it was contributing to 5 electrons. The eta number is 5. However, here it has been assigned an oxidation state of -1. So it means that despite having 5 electrons that it can contribute to 1 electron extra, and therefore our Cp, this sometimes shortened as Cp, will give us 6 electrons. Okay, so in case whereby you see this and you see if you see this, then it is under donor pair method, you must remember that it contributes to 6 electrons. The most important thing also that you need to know is the oxidation number of the metal and how many electrons that the metal is going to contribute. Very important here. In this case, we need to calculate the overall charges of the ligand. Once you have calculated the overall charges of the ligand, then the metal, the electrons have to be contributed by them, or the electrons must be produced by the metal to come and balance those charges produced by the ligands, so that we have an overall charge of 0. Now, the remaining electrons from the metals will be the one that will be contributed to the metal in the overall complex. For example, if I have 2 chlorine, okay, if I have 2 chlorine, and we know that 1 chlorine contributes to a minus charge of 1, all right? And if I have 2, meaning that I'm going to have 2 minus overall. So it means that in this case, I am going to need 2 electrons from the metal to come and balance this -2, so that we can have an overall charge of 0. If I have a overall charge of -1 of the ligands, let's say you add all the ligands and they give you a minus charge overall, it tells you that you are only going to need 1 electron from the metal. If our metal, for example, is in let's say D7, okay? So if our metal is in D7, meaning that we are going to need 1 electron to come and balance this -1 electron, and so that the overall charge can be 0. So meaning that from our D7, we are going to subtract 1 electrons, and therefore the remaining electron will be 6. And that will assume our metal to be in D6. So that is the number of the metals that the number of electrons that our metal is going to produce. And therefore, the oxidation state, or the oxidation number of our metal, will be equal to the number of the electrons that you have required, or you have taken from that metal to balance the overall charge. Having said that, let's look. So we have this complex here, let me D8. So I'll put it aside. So we have our D8. Okay. So now look how many ligands we have. We have carbonyl ligands, and there are 4 of them. And we also have the bromide ligands, or the bromines. There are 2 of them. You can see there are 2. And we have said that 1 charge, okay, 1 bromine has been assigned a charge of -1. And they are 2, so it's going to be -2. carbonyls, which is an L-type, has been a charge and oxidation state of 0. So it means that the overall charge here is -2, which has been contributed by bromine. So therefore, we need 2 electrons from the metal to come and balance these 2 electrons so that it can come to 0. So we're going to need +2 from the metal, meaning that in this D8 we are going to subtract 2 electrons so that we can remain with D6. So it means that after getting 2 metals from Ru from our metal, after we got 2 electrons from our metal, we are going to remain with 6 electrons. So then it tells us that the oxidation state or the oxidation number of our metal is +2 in this case, because we have needed 2 or we have taken 2 electrons to come and balance this charge. So let's look if this complex obeys the 18 electron rule. So now our metal is now in D6 because we have taken 2 electrons to balance this -2, and we have our bromine and there are 2, so 2 times Br. Remember we said that now in the donor pair method the ligands have been assigned -1, so each ligand contributes to 2 electrons, so we have 2 times 2, that's going to be 4 electrons. And then we have carbonyls. How many are they? They are 4, so times, that's carbonyl, and that's going to give us 8 electrons. And if we add them together, how many electrons do we have? We have 6 plus 4, that is 10. 10 plus 8 is 18, so we have 18 electrons. So it obeys the 18 electron rule. Let's look at our second complex. So again, the first thing that we need to do is to calculate the overall charge of the ligands which are here. So how many ligands we have here? We have 1 chlorine and 1 carbonyl. Carbonyl is an L-type that has been charged 0 oxidation state, but halide is an X-type which has overall charge of -1. has been charged -1. So the overall charge here is -1. So then we'll write overall charge. Overall charge is equal to -1. Then it means that we need 1 electron from the rhenium metal so that we can balance this -1 to bring it to 0. So rhenium is in which group? Let's check. So rhenium is in D7. So our rhenium is in D7. So we're going to have D7 minus. So from D7, we are going to subtract 1 electrons, or we are going to take 1 electron so that it can balance this -1. So we're going to say -1. Then we're going to remain with D6. Okay. So this is what we are going to, or this is what is going to be contributed by the metal. So our rhenium, that is going to be D6. And then we have our chlorine, it is 1. So it's going to contribute to 2 electrons. Remember, this is a donor pair method. Each X type contributes to 2. And then we have our carbonyl, which is, how many are they? There are 5. So we're going to 5 times that carbonyl, and that's going to give us 10 electrons. And then we have to add the total number of electrons. So we have 6 plus 2 is 8, 8 plus 10 is 18, so we have 18 electrons. So it tells us that our complex has obeyed 18 electron rule because it has the sum of the electrons possessed, or the sum of d electrons possessed by the metal, plus the sum of all ligands contributed or donated electrons should add up to 18, just like we have seen. So this is how 18 electrons rule works. Something that I want to insist on is that no matter donor pair method or neutral ligand method, they will add up to 18. Okay, they will add up to 18. And let's take an example in this case. Okay, let me wrap. So let's take an example in this case. whereby the same, we want to prove if the two methods can really give us the same number of electrons. So let's just take this one here, complex number 2. So the same we want to do using neutral ligand method. Okay, so we have rhenium we have said it is in D7. Okay, so we have our rhenium which is in D7, and we have chlorine. So we have chlorine, and chlorine contributes to how many? It contributes to 1 electrons, is 1. And then because it is X type in neutral ligand method contributes to 1. And then we have carbonyls. How many are they? There are 5 times that number of carbonyls, that is 10 electrons. So let's add how many are they? 7 plus 1 is 8, 8 plus 10 is 18 electrons. So it tells you no matter which method you use, you will still get the same number of electrons. Just like in this case, ruthenium we found it was D8, so that was D8, so that is 8 electrons. And bromine here are 2, so that's gonna be 2 electrons. And then carbonyl here are 4 times 2 is 8, so you're gonna have 8, a total of 8 plus 2 is 10, 10 plus 8 is 18. It will still give us 18 electrons. So what we are trying to prove is that no matter which method you use, it will still give you the same number of electrons. Thank you so much. I hope we are together. See you in the next video. Hey, remember to subscribe, share, and like the video so that each and every time we make new uploads, you'll be the first one to get notified. Thank you. Wish you all the best.